And hi everyone, my name is Chendong Wang, and I'm a math student from the University of Minnesota. So today, my co-author Anna and I will give a talk about our project, efficient volumetric video streaming. This is a joint project with George Mason University. Okay, so we all enjoy videos, and nowadays the video content we have been watching is evolving. So we have been familiar with the traditional video for a long time, which is obviously two-dimensional, and the user have no control on the content they watch. So recently, 360-degree panoramic video is getting more popular, and the video is still two-dimensional, but the content is wrapped onto a sphere, so the audience can have 3 degrees of freedom, which is the low pitch and yaw, while the video is being played back. So in this paper, we focus on a new video type called volumetric video. Basically, it's the kind of video content composed of 3D animated point cloud or mesh. So the point cloud-based video consists of vertex, which have 3-dimensional coordinates and colors. For mesh-based video, it consists of a big number of polygons in 3D space. So the points and the polygons are changing over time to depict sequences of frames. The volumetric video is also of 6 degrees of freedom that allows the user to control not only low pitch and yaw, but also the camera position. So it provides immersive telepresence experience. So in the demo of volumetric video here, the user experience is very immersive since the video content is adjusted as the audience makes its move. So in this study, we focus on volumetric video streaming in wireless or mobile network. Our main challenge lies in the high bandwidth utilization that may consume hundreds of Mbps. So in the literature, dash-based streaming that consider bitrate adaptation based on the network condition is studied. And there's another work called Vivo that makes prediction on user viewport to reduce the content to be fed. So in this study, we try to explore this following question. Can we leverage the computation resource to mitigate the bandwidth consumption? So in the computer vision community, there's a technique called super resolution, which allows us to train a convolutional deep neural network that can enhance the visual quality of a 2D image. So on a commodity GPU, we can convert images from low resolution to high resolution at about 30 frames per second. So recently, the super resolution research has been extended to 3D point cloud. The point cloud super resolution is also a learning-based approach to enhance the point cloud density while maintaining the outline. The video will look more concrete with higher density, and thus the video quality will improve. So just with such reconstruction capability, we can surely reduce the bandwidth usage and also be able to achieve reasonable reconstruction error. So we conducted a pilot study that applying the SR model to a volumetric video recorded by 3 RGB cameras. The video shows a person giving a talk and is composed of over 3,000 frames. So in each frame, there are about 100,000 points. The experiment is conducted on a desktop with high-end commodity GPU, and we upsampled the video content by 4 times with PUGAN, a state-of-the-art 3D SR model. And thus, we are able to identify the following limitations. First, the 3D SR inference is quite computational intensive. Most 3D SR models can achieve only 0.1 frame per second, which is far from acceptable on mobile devices. So second, if we do the super resolution frame by frame, the upsampled points may shift randomly in consecutive frames, so which will lead to the visual inconsistency. Third, there's also a lack of color support for upsampled points. So in this paper, we try to address these limitations with our own approach. So we aimed at building a holistic system under these 2 scenarios. On one hand, we can design an edge-assisted VR system. So the VR headset is connected to an edge server, and the edge is responsible for fetching, super resolution, and rendering. So on the other hand, we can give a standalone solution where the mobile devices like VR headsets are required to do the super resolution and rendering themselves. So next, Alan will introduce more details of our method.
Hi everyone, my name is Alan Zhang from the University of Minnesota Twin Cities, and I'm a second-year PhD student. So inspired by our pilot study on existing 3D SR models, we come up with a system called Volume SR, efficient volumetric video streaming through super resolution. Volume SR brings SR enhanced volumetric video streaming from theory to practice. And to make it work, we consider these following 4 aspects when designing Volume SR, including speeding up 3D SR, improving visual consistency across frames, coloring SR results, and adapting to network and computation resource. So the first one, speeding up 3D SR. In order to meet the real-time requirement for video streaming, which is at least 30 frames per second, we need to speed up the entire 3D SR process. So a straightforward way we can easily come up with is to simplify the 3D SR model. So to have a better understand which part we need to focus on, we can first take a look at the runtime performance breakdown of an off-the-shelf 3D SR model. For example, here we profile the inference time of a state-of-the-art 3D SR model called PUGAP. And the table shows that the bottleneck comes from the feature extraction stage, which takes 78% of the entire inference time. So after knowing our simplification target, now we can strategically make our optimizations. For example, we can remove the layers that contribute little to the final results. And we can also replace the operations in the feature extraction stage with more efficient operations. So our high-level principle is to reduce inference time as much as we can and do not hurt the inference accuracy too much. At the same time, we find that the patch generation in existing 3D SR incurs high overhead. So this picture shows a typical process of existing 3D SR. To make sure the model size is small enough to run on a commodity desktop GPU, existing 3D SR divides the entire point cloud into small patches and use patches as basic upsampling units. However, the generated patches may have overlaps because of the algorithms they use to generate. So after upsampling, a farthest point sampling algorithm has to be applied to remove the overlapped areas. So the overhead comes from the overlaps. First, the points in the overlapped areas may be upsampled multiple times, which is the waste of the computation resource. Second, additional computation resource has to be used to remove the overlapped areas after upsampling. So a potential method to speed up is to simplify the patch geometry shapes so that we can remove the overlaps and save computation resource. For example, we can simply dividing the entire point cloud space into small cubic grids, and each grid with points can correspond to a patch. At the same time, we also make 2 other observations of a point cloud based on volumetric video and existing 3D SR models. So first, a point cloud is a set of unstructured points, which means we can easily merge 2 point clouds into a single one. Second, the output points of existing 3D SR models are very different from the points of the input. So that's because of the complex and the nonlinear operations taken by 3D SR models. So a potential way to further speed up 3D SR in our system is to reuse the SR input and overlay it onto the SR output. For example, here, if we want to upsample 25,000 points to 100,000 points, we can first upsample the frame to 75,000 points, and then overlay the low resolution input to the model's output. Besides the 3D SR itself, we can also apply some machine learning and 3D computer graphics techniques to speed up 3D SR in our system. For example, here, the viewport adaptation is a promising way. So in 360-degree video streaming, the panoramical scene is divided into small cells. then the viewport prediction technique is applied to predict the user's future viewport, the longitude and latitude. Then only the cells inside the predicted viewport or around the predicted viewport will be fetched from the server. So this method helps save bandwidth for 360-degree video streaming. And in SR enhanced volumetric video, we can apply a similar idea. For example, we can build some machine learning models to predict the user's future view frustum and only upsample the patches that are inside the predicted view frustum. So in 3D computer graphics, the view frustum is a region of space in the modeled world that may appear on the screen. However, we believe it's more challenging to apply viewport prediction in volumetric videos than applying it to 360-degree videos because it requires accurate prediction of the user's 6 DOF motions, which is much more than what we need to predict in 360-degree video. After speeding up the 3D SR, we now consider improving visual consistency across frames. So a potential way is to consider visual consistency in the loss function of the SR models. We also explore another approach, which is reusing SR results. So as shown in this picture, we may use the motion vector to approximate the transition of the points in the patch of the same position in 2 consecutive frames. So a motion vector is an approximation of how the points in a patch translate to the points in another. So this brings us 2 advantages. So first, it brings a smooth transition so that we can mitigate the visual inconsistency across frames. Second, it also brings less computation overhead because we do not have to always doing super resolution for every patch. However, the approximation may be inaccurate if the geometry shapes of 2 patches are very different. So for video on demand streaming, we can offline decide which SR results can be reused and pre-compute all the motion vectors we need. So the next aspect is coloring SR results in our system. We explore 2 approaches. The first one is modifying the SR model and let the SR model to infer a point position and the color at the same time. So this approach is accurate, but also heavyweight because the model needs to infer more attributes of each point. The second approach is to approximate a point color through, for example, interpolation. And we can use the color information in the low resolution frame to help us. So this method is lightweight, but less accurate than the first one. The last aspect is adapting our system to different network and the computation resources. So in traditional video streaming, the designing of an adaptive bitrate algorithm, an ABR algorithm is important because ABR algorithm can adapt the video quality to different network conditions. When designing volume SR, we face a bigger challenge. That is, we need to adapt our video quality to different network conditions and different computation resources simultaneously. So there are trade-offs between these 2 kinds of resources. If we use more bandwidth to stream high quality point clouds, we can spend less computation resource to do super resolution. In the other way, if we use little bandwidth and stream low resolution volumetric videos, we have to spend more computation resource to upsample the contents. Another critical challenge is modeling users' quality of experience of SR-enhanced volumetric videos, so that we can use our QE model to guide the design of our adaptation algorithm. We believe that the QE model of volumetric video, SR-enhanced volumetric videos is much more complex than that of traditional 2D videos because it involves more factors. For example, point density, viewing distance, the distortion introduced by 3D super resolution, and etc. We have implemented a part of our optimizations and conducted evaluation of them. So in our evaluation, we consider the mobile-only streaming scenario. So for our evaluation setup, we use a Jetson TX2 embedded system board. And we use the volumetric video we mentioned in our pilot study and upsample the entire video from 5,000 points per frame to 20,000 points per frame. So the SR ratio is set to 4. We choose a state-of-the-art 3D SR model called PUGAN and simplify its model and patch generation. So the table shows our current results. We consider 3 metrics: the memory usage when doing super resolution, the frames per second for SR, the entire video, and the average SR accuracy for the entire video. So for FPS, higher is better, and for the other 2 metrics, lower is better. So our results shows that by simplifying the model and the patch generation, we can already drastically improve the FPS and greatly reduce the memory usage. Surprisingly, we also achieve a better average accuracy than the vanilla PUGAN model. To recap, we conducted a first study on efficiently streaming volumetric video contents through super resolution. And to bring it from theory to practice, we consider several aspects when designing our system, including speeding up 3D SR, improving visual consistency across frames, coloring SR results, and adapting to network and the computation resource. We also propose several optimizations based on the unique properties of volumetric videos. So, and our preliminary results show that a part of our optimizations can already achieve great runtime performance improvements and a good SR inference accuracy as well. So currently, we are developing the entire volume SR system. We also plan to conduct extensive evaluations using more volumetric videos and real user 6DLF movement and different network conditions. So that's all for me. Thank you very much for listening.